So next up, we've got Manish Singh, who is the CEO at memQ. Thank you.
Thank you, Will. Great. So I lead the team at memQ. We are a startup based out of Chicago. We spun out of the University of Chicago from research that was done at University of Chicago and Argonne National Lab. The founders come from a semiconductor background, so we bring a lot of that semiconductor ethos to the tech development that I'll talk about in a second. The problem that we are after is solving this quantum network problem. You've heard about quantum sensing. You will hear about quantum computing. In both of these set of technologies, both of them are capable of really, really important breakthroughs. But in both these cases, we have development that's focused on development of individual modules. Modules that are very powerful in themselves, but are limited by the size of how large a module can you build. And these modules have a size limit that's coming up. The only way to work around that is to develop interconnects that allow you to connect two quantum computers via this optical interconnect in a fashion that allows you to preserve the entanglement properties, to preserve the quantumness of these two modules. And the vision here is that of a memQ chip, a memQ system on a chip that allows you to connect 2, 4, 8, 16, any number of points on a network. And on either end, you could have a quantum computer, you could have a quantum sensor. And the great thing about quantum is the more of these you put together, the power grows exponentially. In compute, the power grows exponentially. Your computers become much more powerful very, very fast. And in sensing, your sensing capabilities increase. They go beyond the physical limit every time you add another sensor to the network. So this is what our chip would look like. You'll have an optical coupling capability that can bring in single photons, that can bring in classical communication, the way we know how to do very well in our current technologies. It'll use silicon photonics, integrated silicon photonics, to route these photons to regions which we identify as quantum resource generator. So these generator capabilities that can give you single photons, that can give you entangled photons, that can generate cluster states. And then capabilities that allow you to measure and control. And capabilities, and this is where memQ comes in, to store these quantum states. Without being able to store these quantum states, you cannot create a quantum network. And the reason's very simple. It's the inherent quantumness of it. It's the fact that you cannot copy quantum states. That's what prevents you from creating a network the regular way. And this is the key technology we are developing. The quantum memory, that's where we get our name from, for memory qubits. That's where memQ comes from. Now, I'll tell you a little bit about the engineering, because we have a very diverse crowd here. The way we work is we integrate our qubit layer. Our qubit layer consists of a very thin oxide film. That's the key technology at the heart of memQ, protected by multiple patents. Allows these single erbium atoms to sit inside an oxide layer that can integrate directly with silicon. And now you can use the CMOS processes to develop all the components that you need to get to that system on chip that I talked about. So you can do component design, you can do characterization really, really fast. And that feedback optimization loop is what memQ has been focused on over this last year. The qualified chips from here go for cryo testing, go for packaging, because that's where the quantumness becomes really apparent. You need to be able to be at temperatures that are about 4 Kelvin or lower. And the qualified designs, they go out for foundry tape out. We have taped out our first 300 millimeter wafers, and we are waiting for that to come back. So here's the opportunity. You have quantum sensing on which you have multiple companies that are working on that full stack. You have quantum computing that has a wide range of companies, from the biggest names to new startups that are working on that problem. And the most important pillar that's missing is that of the quantum network. We don't have the interconnect hardware. We don't have the interconnect control layer. We do not have the network layer. So this is the opportunity that memQ is after. This is what will unlock the full application of quantum technologies. You cannot get there by using a single module. You need to be able to connect tens and hundreds of these modules together. And this is how we see it. These are the pieces that come together to make that happen. These are the pieces that create that full stack of quantum networking that we are after. You need the physical components. You need the capability to control this in the unique environment that these quantum memories need to be in. You need to be able to create the interconnect that allows quantum computers to connect to that network. And you need to be able to orchestrate entanglement distribution across a network. The components for us, it's built upon the material science technology that memQ's founders developed. The control system that controls the generation and distribution of the quantum states. Interconnect is what allows you to connect this to a quantum computer, to a quantum sensor, and orchestration, again, is what allows you to manage entanglement over a network. Now, our approach, we've been very focused on the components. The components that you see there is what allows you, if I were to pick one item in the quantum technologies that's the equivalent of transistors as we see today, this is what I would pick. This photonic cavity is what allows you to engineer that interface between a photon and an atom. With CMOS technology, we got really, really good at controlling the flow of electrons. We know exactly how to engineer that over really, really small distances. The next frontier is where we can control the interaction between a single photon and a single atom. That's what we're building towards. And that's being able to leverage, being able to harness that physics is what's unlocking the new capabilities that quantum technologies is used to refer to. That's where the power comes from. So what you see here is the prototype of some of the devices that we've developed. The second stage of development is the building of that interconnect, starting to develop that system on a chip that I told you about, and ultimately that quantum network where you're connecting computers, sensors, and quantum clocks together. Now, what do we need to get there? You need the capability to store quantum states. This translates to the need for quantum memory. That's where memQ comes in with its erbium-based quantum qubits. There's a need for interconnect. And the interconnect needs to function in a way so that it preserves the quantumness that needs to be established between two modules. So you need a resilient quantum state. And the quantum state that's the most resilient is the photon. Doesn't interact with anything, travels many light years, and you can still, without any changes in its original properties. You want very low loss transmission because quantum information cannot be copied, and we're still far away from what would be error correction in this area. You need to be at a wavelength where you minimize the losses. You need to operate at the wavelength around which our whole communication infrastructure is built. You need to operate at the telecom C-band wavelength. And one of these devices won't be enough. Two of these devices won't be enough. You will run into a scaling problem again if you start from there. So you need a platform that allows for high density integration of the components, and this is where you need to leverage the chip manufacturing processes. That's why we have started with integrated silicon photonics, so we don't see that scaling bottleneck. We start with a solution that is scalable, and we solve for the rest. And you need a shit ton of supporting technologies, because you can't develop a laser at whatever wavelength you're operating at. You can't develop control systems at whatever wavelength you're operating at. And the richest ecosystem exists around 1550 nanometer, because that's how all our communication happens today. So this is why I'm really, really excited about the things that memQ is doing. Our memory is erbium-based. That allows us to work directly at the telecom C-band. And the platform that I showed you the picture of before, that allows you to integrate directly with silicon photonics. So you got the scalability of CMOS. You got the quantum memory that's critical for quantum state storage. You got your C-band photons with very low losses. And you got the integrated silicon photonics that solves for the scalability. Now, the way we see it, you got the generator, storage, and distributor. All of this comes together to build that full stack quantum network that I was telling you about. And that has multiple applications. There are areas in PNT. There are niche compute applications for memory. There are distributed quantum computing and quantum sensors. Out of these, the most powerful application is that with distributed quantum computing and distributed quantum sensors. Now, let me tell you a little bit about what we have done over the past year. So we made our first hire at the beginning of 2023, and since then we have built a really, really strong team of A performers. We built our quantum state generator. We did quantum state entanglement distribution across 132 kilometers. That's something that we don't talk about as often, but there's a fantastic thing made possible because of the Chicago quantum network that exists right in our backyard in Chicago. So this is fiber that's buried in the ground. It sees the seasons. It sees trucks roll on it. It's right by the highway I-55. And the entanglement statistics are beautiful. As I told you, we've done our foundry tape out to 300 millimeter wafers. Like I said, the scalability problem is something that you don't solve at the end. You solve for it at the beginning. And then there's IP protection for all the technology that we are developing. There's scientific validation too. There are 3 papers over the last year that memQ has led. And we have demonstrated some early traction on this technology that we have developed working with some key partners. This is the team that has made all that happen. There's a little bit of a theme going on here. We refer to the Chicago Midwest quantum ecosystem as the quantum prairie. These are the lions hiding in the prairie. You see the beautiful Lake Michigan in the background. Yeah, and this is the summary for you guys. The founders come from the semiconductor industry. I spent years at TSMC. One of our founders spent multiple years at IBM. We did the research that this is based on comes out of University of Chicago Argonne National Lab. That's the same region where a very large chunk of the National Quantum Initiative funding went. I think the total funding coming from the state and the nation comes up to about very close to $1 billion. We have 6 full-time employees, so the team is small. The team is very focused on solving some of our key problems. There are patents protecting us. We're working with a decent amount of funding. There are close to 20 papers now that support the technology that this is based on. Yeah, and we are on a mission to connect everything quantum and unlock its true potential. By the way, we are hiring a photonic design engineer if anybody is looking for a job there.